I'm Shannon Bourke. Today during my talk, I will tell you a little bit about the Physics 101 class and the lab. I will explain the history of Chladni patterns. I will describe the construction of the pattern generator that I built. I will talk about generating patterns. I will show you some results, and then I will sum it all up. Okay, so first, the Physics 101 class. The Physics 101 class is Physical Science and the Arts. It's a general education course that attracts about 300 students a year. A very high percentage of these students are music majors, thus a substantial portion of the class is dedicated to sound and music. The focus is on conceptual understandings and working to develop observation and measurement skills. This class has a lab component to it. And one of the labs focuses on Chladni patterns. So during the lab, they use two different methods to get the plates excited. The first method that they use is with a violin bow. They'll take a violin bow, run it along the edge of a plate. The other method they use is a mechanical driver. The mechanical driver is attached to the center of the plate, and then we connect it to a function generator. And this function generator you can change the frequency on, and that will get the plates moving. These patterns form when the plate is moving at the resonant frequency of the plate. There are multiple frequencies that this will occur at. And this forms because the sand goes to the areas of the plate that are not moving. This method was first developed by Ernst Chladni. This is who Chladni patterns are named after. He was alive from 1756 to 1827. He is very well known in acoustics, and acoustics is the study of sound. He was known for the method of bowing that you saw in the previous slide that our Physics 101 students use. Miss Mary Waller, Dr. Mary Waller, actually, she continued this work more than 100 years later. Her date of birth is not well known, but she did pass away in 1959. And she picked up his work and used dry ice. She was a professor of physics at a college for medical sciences. It is said that she got her idea for the inspiration for doing her work because while she was out one day, an ice cream delivery guy on a bicycle, the little chips of the dry ice that were being used to keep the ice cream cold were flying onto the bell, and the bell started ringing. And this got her thinking about why this happens. So she used this method to start making the patterns form. And as you can see down here, she got really, really nice pictures and patterns. We used her for our inspiration of developing our pattern generator. We wanted to be able to choose where we could excite the plate, because with the mechanical driver, it was only excited in the center. With the violin bow, it was only excited at the edge of the plates. So we did not want to have to rely on always having dry ice chips available. So we decided to go ahead and design our pattern generator. Our pattern generator is based upon a piezoelectric motor device. A piezoelectric motor device is about 1 inch tall and has a very small cross-sectional area. So it takes and receives electrical signals, and these electrical signals will cause the motor to move in and out. And you will start getting vibration of the plate. Because we needed a very small surface area, exactly 1 point, exciting the plate, we have a little sapphire hemisphere that has been epoxied onto the edge of that motor. The motor is very fragile and is only attached by epoxy onto the base plate. So we built a piezo shield, which is seen right there is the piezo shield. And then there's the piezo mount plate that the piezo is attached to with a little hole that lets wires go through down to the BNC connector. The BNC connector is an electrical connector that allows the current to flow through to the function generator and will tell the piezo motor how fast it's supposed to be moving. We needed some relatively inexpensive housing for the device, so we chose PVC pipe. as you can see here, this is the PVC pipe, the name on it. We have affectionately called our device Charlotte. So the experimental setup is down here. We have a thin plate that is resting on four rubber bumpers. When we were reading Mary Waller's writings, she said that she rested her plate on fine soap mat and made it sound that it was very critical to have the right material to rest your plate upon. We could not discover what fine soap mat was. Apparently this is a term that was used back then, but is not common now. So we took our best guess, and we came up with these bumpers that are hemispheres, so you have the smallest contact area of the plate as possible. Because if it's too large of an area, it will damp out the vibrations, and you will not form these patterns anymore. We have tried 3 different stiffnesses: extra soft, soft, and medium soft. As I said, I actually physically constructed the parts myself. We have a machine shop down in the basement of the physics building. I used a mill, a lathe, and a drill press. I actually learned how to use them, so I myself did get to have experience using them, which was the first time, so that was really fun. The first piece I constructed was the piezo shield to protect. The second thing I did was the piezo mount plate, so I could actually have something to mount the piezo onto. And finally was that coaxial plate, which was at the end to let the connector at the end. And there is a picture of the piezoelectric motor on the base plate. As you can see, it is very tiny. Before I could construct, I had to make scale drawings of all of my parts. So this is just an example of the piezo one. As you can see, there's a top, bottom, and side view with all of the measurements drawn out very accurately. Okay, then I have a quick video here.
Try double clicking.
What?
Try double clicking.
Okay. This video shows how the patterns were generated. As you can see, it gets louder, or as you can hear, it gets louder when it hits that resonant frequency, and the patterns will form almost instantaneously.
Lower left.
Sorry, I am a PC user, not a Mac. I have a few pictures of some of the different patterns I formed. So I'll just go through them really quickly. On a 10-inch by 10-inch plate, I started with a 10-inch by 10-inch plate, went down and decreased the length of the plate by 1 inch, all the way down to a 10-inch by 3-inch plate. We wanted to see what would happen. And there's an 8-inch by 10-inch plate, a 9-inch by 10-inch plate, and a 5-inch by 10-inch plate. So they all have very symmetrical patterns, and they are very nice, clear patterns. Here are some results. I excited all of these plates at the center, and they were supported by 4 rubber bumpers that were at each of the corners. I thought that as you decrease the size of the plate, you would need a higher and higher frequency to get this plate vibrating and form these patterns. This frequency here in this column is the lowest frequency at which I was able to find a nice, clear, defined pattern. I started out at 1,000 hertz because of all of my experience in teaching the lab and working with these Chladni patterns. So I started at 1,000 hertz and increased the frequency up until I got a nice, clear pattern. As you can see, there's a lot that are around 2,500 hertz, but yet there's a lot that are not. So there was no clear pattern on what happened, which was something I did not expect, so I need to do a little bit more work with this to find out. So as part of my project, as Dr. Behringer explained, I started working on this over the summer. And part of the project reading papers to learn the historical background of Chladni patterns. I designed the device to generate the Chladni patterns. I constructed the device, and I generated the patterns. In the future, I will work on modeling using finite element analysis, and I will build a second transducer. There is an apparatus contest at the American Association of Physics Teachers that we will be entering this in. On a final note, I leave you with a colorized version of Chladni's original drawings. Thank you very much. Are there any questions?
Any questions?
Yes.
What is finite element analysis?
It is a computer program. That is all I know about it right now. Yes.
You said you hooked it to a function generator. Were you using a sine wave or square wave? Or...
It outputs a sine wave.
Other questions?
Yes.
Does the placement of the